let f be the function f of x equals 3x minus x squared. Find f prime using the limit definition. Well, we know the power rule, so let's quickly find what the answer is the easy way. So f prime of x is 3 times 1 minus 2x. All right, so we know what's supposed to come out to. Now let's do it using the limit definition. So the limit definition of the derivative says that f prime of x is the limit as h goes to 0 of this ratio, f of x plus h minus f of x over h. All right, so that's the limit as h goes to 0. H is h. Now what's f of x plus h? Here's our original function f, so I'm going to rewrite this function with x plus h plugged in for every x. All right, and then we'll do minus f of x. Don't forget parentheses. Okay, can we plug in 0 for h? No, because we've got an h in the denominator. So this won't give us a well-defined result. We'll have to do some algebra, and then finally we'll get to a place where we can plug in 0 for h. All right, what algebra can we do here? Well, we can distribute this minus sign, so that turns into minus 3x and plus x squared. We can distribute the 3x plus 3h minus, and we can FOIL out x plus h squared, which will give us x squared plus 2xh plus h squared. Let's see what simplifies. Let's see what cancels. All right, that should be 3h. So we've got 3x plus 3h minus x squared minus 2xh minus h squared. I was just distributing the minus sign here. Minus 3x plus x squared. Okay, what's going to cancel here? So we've got a minus x squared and a plus x squared. And let's see, we have a positive 3x and a minus 3x. Let's see what's left after canceling those. So we've got 3h minus 2xh minus h squared is what's left in the numerator. All right, and now every factor in the numerator, or every term in the numerator has a factor of h. So this is the same as limit h goes to 0. You can pull out a factor of h. 3 minus 2x minus h all over h. Now can we plug in 0 for h? Almost. Still have an h in the denominator that'll give us a 0 in the denominator if we plug in 0 for h. So we have to do a little bit more algebra. Not much. Really just one step. All right, so we have an h in the numerator, h in the denominator. Those can cancel. So this is the limit as h goes to 0, 3 minus 2x minus h. All right, and now finally, we've reached a situation where you can plug in 0 for h without getting a 0 in the denominator, something undefined. So this is 3 minus 2x. And notice I stop writing limit once we plug in 0 for h. All right. Next, let's compute the derivatives of some functions that take multiple steps. We'll have to use product rule, quotient rule, chain rule in some combination. All right, so for this first one, the derivative of e raised to this quantity, that's the product of t squared and root 1 minus t. We have the outside function. The outside function is e to the t. This is last by order of operations. That's how we decide what the last outside function is. All right, so then this will be the derivative of the outside function, but instead of having t plugged in, we'll have t squared 1 minus t plugged in. All right, and then we have times the derivative of the inside function. All right, now to take the derivative of the inside function, I will need product rule, because we have the product of functions, t squared times root 1 minus t. So this equals e to the same stuff times, okay, first I'm going to write down just what the product rule tells me, and then I'll work out the details. So the product rule tells me it's the derivative of the first function times the second function plus the first function times the derivative of the second function. Okay, so we only have two derivatives left to do, and one of them's easy. So this is e to the same stuff. All right, times 2t square root of 1 minus t plus t squared. All right, so I'll need a little chain rule for this, but it'll be 1 over 2 square root of 1 minus t times the derivative of 1 minus t, but that's negative 1. All right, there's our derivative. Simplify if you like to do so. Next, we're looking at the derivative of this terrifying function. We have a seventh root is the last step. Is the seventh root of x, or x to the 1 over 7. And then there's more steps in here. Let's peel it back a layer at a time. So it's going to be helpful to rewrite this expression using properties of exponents to make it easier to use the product rule, the power rule rather. So if we raise this thing to the 4th power and then we raise it to the 7th root, we take the 7th root rather, that's the same as raising it to the 4 over 7th power. So from here to here, I haven't done anything really mathematical, just rewrote it in a way that's going to make it easier to use the power rule. So the first step in our chain rule problem is power rule. To the, let's see, what's 4/7 minus, that'll be negative 3/7. All right, and then chain rule, we have to do times the derivative of the inside function. Okay, this feels like progress because now we're taking the derivative of a less complicated function. All right, so the derivative of natural log. So this is our new outside function. Looks like natural log of x. Its derivative is 1 over x. So we'll write 1 over x cubed plus 2x. But then because of chain rule, we have to do times the derivative of our new inside function, x cubed plus 2x. All right, but thankfully this one's easy because it's just the derivative of a polynomial. All right, so then that's times 3x squared plus 2. And there's our derivative. Our next derivative is the derivative with respect to y of the product of 3 functions, y to the 8, 8 to the y, and log base 8 of y. I know how to differentiate these 3 functions. I just need to figure out how to handle it when they're multiplied all together. Let's arbitrarily put some parentheses around part of these functions. So let's consider this function that we're taking the derivative of to be the product of 2 functions where we have this is f and this is g. So then the product rule tells us that the derivative of this function will be the derivative with respect to y of the first function times the second function plus the first function times the derivative with respect to y of the second function. Okay. Well, One of these derivatives is easy. So we have plus y to the 8, 8 to the y, and then this turns into, it's almost just 1 over y, but we have natural log of 8. All right, and then we have some stuff times log base 8 of y, and this is the last bit of work we have to do. We'll have to use the product rule again to take this derivative. So again, I'll write down what the product rule tells me. This will be y to the 8 prime, 8 to the y, plus y to the 8, 8 to the y prime. I hope you can read that. All right, the derivative of y to the 8 is 8y. So we have 8y times 8 to the y, y to the 7. 8y to the 7 times 8 to the y, plus y to the 8 times, now the derivative of 8 to the y is almost just 8 to the y. But we get this times natural log of 8 that pops out. And then we're done. It seems harder in the beginning than it does at the end. All right, next up is an implicit differentiation problem. We've got this relationship between x and y to the 4th plus xy squared equals -5. Now you cannot solve this thing for y. But even though it's not a function, even though y is not a function of x, we can still use calculus to find equations of tangent lines. So let's find an equation of the tangent line to the graph of this thing at the point -6, 1. All right, so an equation of a line. I find it convenient to use point slope form. All right, so here m, as usual, is the slope. And the point x1, y1 is any point on the line. Well, we've been given 1 point on the line, so let's use x1, y1 equals -6, 1. Though there are infinitely many points on this line, and you could use any of them to get a correct answer, why not use the one that we've been given? All right, next we need the slope. So how do we find the slope? It's calculus. So we'll find dy dx. And then we'll get a formula for the slope, and we'll plug in that point x is equal to -6, y is equal to -1. All right, so starting from our given equation, we'll take the derivative with respect to x on both sides. Okay, well, the derivative with respect to x of -5 is still 0, but we need to be a little bit careful on this side since we're implicitly treating y as a function of x. So instead of just getting 4y to the 3rd for the derivative of y to the 4th, we'll get 4y to the 3rd times the derivative of the inside function, which in this case is y, because we're treating y like a function of x. So you can imagine that the inside function is y. So just like according to chain rule, the 4 comes down, the new exponent is 3, and then it's times the derivative of the inside function. Okay, and what's the derivative of y with respect to x? Well, it's just dy dx. All right, and now we have to be careful when we're computing this part of the derivative, because x is a function of x, and y we're treating as a function of x, so we need the product rule. All right, so I'll write down what the product rule tells me. It's going to be the derivative with respect to x of the first function times the second function, plus the first function times the derivative with respect to x of the second function. All right, the derivative of x with respect to x is 1. Notice that here, the variables match and the derivative is 1. Here, the derivatives did not match, and we got this dy dx that popped out. The variables match, rather. Okay, so we take the derivative with respect to x of x, we get 1 y squared plus x, and then the derivative of y squared with respect to x is 2y, but then because we're doing implicit differentiation, observe that these variables don't match, we get 2y then times dy dx that pops out because of chain rule. Okay, at this point the calculus is done. Let me rewrite that a little bit more neatly. So at this point the calculus is done. We're going to solve for dy dx like a variable. So let's see, I'll subtract y squared from both sides. Then I will factor out the common factor of dy dx. All right, and then finally, we'll divide both sides by this whole business to isolate dy dx. Okay, so this is a formula for the slope at point xy on the graph. So it's the slope of the tangent line at point xy on the graph. Our particular point is x equals -6, y equals 1. Is that... Yep. X equals -6. Y equals 1, dy dx equals negative, let's see, 1 squared, so -1 over 4 times 1 to the third plus 2 times -6 times 1. So that's -1 over 4 minus 12 equals -1 over -8 equals 1 over 8. All right, so now we have everything we need to write down our solution. All right, and I say find an equation of the line. I don't require you to put it in any particular form. So if you like rewriting it in slope-intercept form, then be my guest. All right, word problems, here we go. A square bottom box must be constructed with a volume of 100 cubic centimeters. Square bottom box, okay, so let's see. We've got the bottom is a square, and we have, here's our box. Okay, square bottom. The material for the 4 sides of the box costs $2 per square centimeter. Okay, so we have 4 times side at $2 per square centimeter. While the material for the top and bottom costs $3 per centimeter. So we have 2 times the top, bottom, here's the top, at $3 per centimeter cubed. Find the dimensions that minimize the cost of the box. Okay, well, if we're trying to minimize something, that's an optimization problem. Sometimes we're trying to maximize it, sometimes we're trying to minimize it. All right, so let's write an equation for the cost, and then we'll write a better equation, and then we'll write a better equation, and so on, until we have something we can do calculus analysis on. So let's see. The total cost is going to be 4 times the cost of sides plus 2 times the cost of the bottom. All right. How much will a side cost? Well, the cost of a side, it's $2 times the area in square centimeters rather. And the cost of the top will be $3 times the number of square centimeters. So now I'm going to need to add some variable names here to this drawing of our box so that we can upgrade our equation here to something we can actually use. Let's call the side lengths x, and because it's a square bottom box, they're both going to be x, and then that leaves the other dimension to be determined is height. All right, so now we can have cost. It's looking more mathematical. So we've got 4 times $2 times, let's see, what's the area of a side? So the area of a side has has length x in one direction and has height h in the other direction. So this will be x times h plus 2, because there's the top and the bottom, at $3. Okay, and the area of the top and area of the bottom, it's a square with side length x, so it's going to be x squared. Okay, this is pretty good. We're making progress. There's one thing we need to improve before we finish, though. Here we have 2 variables. We've got h's and x's. We want to somehow rewrite this as an equation with just one variable. And in order to do that, we're going to have to use some details from the problem that we haven't used yet. So we haven't used the fact that the total volume of this thing is supposed to be 100 cubic centimeters. So what's the volume of a box? It's length times width times height. In our box, these are both x and this is h. So 100 equals x squared, x times h. Which means if we solve for h, it's 100 over x squared, or h equals 100 x to the negative 2. It might be easier to solve for x squared if x squared appeared in both of these. Let's see, we can solve for x squared, maybe that'll be easier, so that's going to be 100 over h, and then x will be square root of that, so 10 over root h equals 10 h to the negative 1/2. So I don't know which of these is easier. We can replace h with 100 over x squared, or we can replace x with, what is that, 10h to the negative 1/2. And just whichever one's easier is the one we'll go with. I think I'm just going to use this one. All right, let's see what we get. So the cost, So the cost equals 4 times 2 times x. Now I'm going to replace h with 100 over x squared. All right, and then we've got plus 2 times 3 times x squared. All right, now we have a function with only x's. Now we're in business. So I can write c of x equals 800 over x. After simplifying, this turns into 8, and this turns into 100 over x, so 800 over x. All right, plus 6x squared. So now we've got a function of just one variable. We can do calculus on it to try to find where it reaches its lowest cost. All right, now that we have a reasonable expression for the quantity that we want to optimize, we can do calculus on it. So c prime of x would be negative 800 x to the negative 2 plus 12x. And now there's two questions we ask about c prime. We ask, is c prime undefined anywhere? Well, c prime of x equals negative 800 over x squared plus 12x. So since we have x's in the denominator, it's undefined at x equals 0. But what kind of box would have width 0? Doesn't make sense. So we can discard that part of the result. The next question we ask is not where c prime is undefined, but can we solve c prime equals 0? Well, let's try. So we've got negative 800 over x squared plus 12x equals 0. All right, let's multiply by x squared on both sides because I hate denominators. So times x squared times x squared. Negative 800 plus 12x cubed equals 0. 12x cubed equals 800. X cubed equals 800 over 12. And that doesn't simplify really nicely. Let's see, common factor of 4, so it's 200 over 3. And then finally, solve for x will be the cube root of that. And centimeters. All right, but we need the height of the box as well as the base. So if we've got our box x, also need to know what the height is, but we have a relationship between height and x that we've worked out already. It was h equals 100 over x squared. So now that we have x, we can immediately find h. So it's 100 over this whole thing squared. Number 5, let h be the function h of x equals natural log of x plus 1 over x. Let's find out where h is increasing and decreasing and look for local extrema. So the first thing we do is take the derivative, because where the derivative is positive, we're increasing, and where the derivative is negative, we're decreasing. So that's 1 over x plus, let's see, what's the derivative of x to the negative 1? So that's 1 over x plus negative x to the negative 2, which equals 1 over x minus 1 over x squared. All right, there's our formula for h prime of x. It might be easier to answer the rest of the question if we do a little bit more algebra on h prime. So if we multiply the first term by x over x to get common denominators, then we get x minus 1 over x squared is h prime of x. So now we ask two questions about h prime. We ask, where is h prime undefined? Well, we've got a factor of x in the denominator here. So h prime of 0 is undefined. But 0 is not in the domain anyway. you can't take the natural log of 0. So it's true that h prime is undefined at x equals 0, but it's not in the domain anyway, so we don't really learn anything from that. The next question is h prime equal to 0? So let's try to solve. 0 equals x minus 1 over x squared. Well, it's not too hard. We can multiply both sides by x squared. Get 0 equals x minus 1. So at x equals 1. All right. So what do we do with this value we found? We divide the domain into zones. So it starts at 0. We'll have an open circle at 0 because there we go. We'll have an open circle at 0 because that's not part of the domain. And then we have a critical point at x is equal to 1. So then we'll check the sign. Of h prime in each zone. So we need a convenient number between 0 and 1. Let's try h prime of 1/2. All right, so let's see. H prime of 1/2, that's 1/2 minus 1 over 1/2 squared. So the bottom is positive and the top is negative. So this is negative. Now we need a convenient value of x that's larger than 1. How about 10? Sure, why not? H prime of 10. H prime of 10. So let's see, that's going to be 10 minus 1 over 10 squared. That's positive on top, positive on the bottom. That is greater than 0. So we are increasing on this interval. All right, what does it look like when you're decreasing for a while, then you reach x equal 1, and then you're increasing after that? That looks like a local min. And let's be sure to answer the other part of the question. Increasing on 1 to infinity, decreasing, not on negative infinity up to 1, just from 0 to 1, because that's where the function is defined. Let's practice with indefinite integrals. So let's integrate the constant function pi. What does that look like? The constant function pi. All right, well, by the constant multiple rule, we can pull out the constant. What's left would just be 1. All right, and do you know a function whose derivative is 1? I think you do. It is x. All right, and don't forget the plus c. Next up, we're integrating a polynomial. We'll just use the power rule a bunch of times, which says that the integral of x to the p dx is x to the p plus 1 over p plus 1 for p not equal to negative 1. All right, so this will be 8 times x to the 5 over 5 minus 6 times x to the 3 over 3 plus 12 times x to the 1 over 1. I'll just write x because it looks like prime. And don't forget plus c. All right, now they're getting a little bit more complicated. So this is, when I first look at it, this rational function whose numerator is x squared and the denominator is 2x cubed plus 9, that's not a function I know how to integrate offhand. But we observe that part of the expression, the numerator, looks kind of like looks a bit like the derivative of another piece. Almost the same. The numerator has x squared. The denominator, if you take the derivative, then you get 6x squared. So it's pretty similar. This suggests it might be a good time for u substitution. All right, so let's try u is 2x cubed plus 9. Then the du would be the derivative of this, so 6x squared, but then dx. And now we can try to rewrite our integral with u's instead of x's and hope it becomes easier. So our integral becomes the integral of x squared over u. But then from this, I get that dx equals 1 over 6x squared du. So I can solve this for dx, treating it like a variable. So then I can replace this dx with 1 over 6x squared du. Now we get some cancellation. These powers of x cancel, and we can pull out the factor of 1/6, which leaves u in the denominator. So after this u substitution, we get a function whose derivative I do know. I do know how to take the derivative, whose antiderivative I do know. I do know how to integrate 1 over u. So that's going to be natural log of, don't forget the absolute value, of u. Don't forget the times 1/6. Don't forget the plus 1c. And we'll just resubstitute in what we had for u. That was 2x cubed plus 9. So 1/6 natural log of the absolute value of the original denominator plus c. All right, another indefinite integral here. So again, I see that part of this looks like the derivative of another part. So negative 2x looks kind of like the derivative of x squared minus 9. So let's let u equal x squared minus 9, which makes du 2x dx, because it's the derivative of u, then with dx on the end, which means that dx is 1 over 2x du. Let's make the substitutions into our integral and hope it turns into an easier integral. So our integral becomes integral of negative 2x over u to the 7, and then we'll replace dx with 1 over 2x du. And we get some nice cancellation here. And this is negative integral of 1 over u to the 7 du, which is easier to compute if we rewrite it as negative integral of u to the negative 7 du. Because now it's more clear how we can use the power rule. So that's negative u to the negative 7 plus 1 over negative 7 plus 1. So that's negative. Just simplifying a little bit, not too much. And we'll put our original u back in. There we go. So we have the same variables that we started with. And of course, it's very easy to check just by differentiating. All right, this problem is a little different. It says use the given facts to compute the integrals a through d. Okay, so then it tells you the integral of the function x from 1 to 4, the definite integral of x from 1 to 4, the definite integral of x squared from 1 to 4, and the definite integral of x squared from 4 to 5. Somehow, this information is enough to compute these integrals without doing any more calculus. Let's take a look. All right, so for a, this integral splits up into the integral from 1 to 4 of x squared dx minus 4 times the integral of from 1 to 4 of x dx. So this is by linearity of integration, the properties of integration, that you can pull out constants and that it splits up over sums and differences just how you would like it to. All right, now I go to the given information on this. We're told what this quantity is, that this quantity is 15 over 2. All right, and then we have minus 4 times, wrong quantity. Okay, so for part A, the integral splits up into the integral of x squared dx from 1 to 4 minus 4 times the integral of the function just x from 1 to 4. And those are both things we've been told. So the integral of x squared from 1 to 4 is 21. And the integral of x from 1 to 4 is 15 over 2. All right, so that's 21 minus 30, which is negative 9. Okay, B. What was B? B is the integral from 1 to 4 of 1 minus x dx. No, x, 1 minus x dx. All right, so this doesn't look exactly like any of the formulas, any of the given information, but with a little bit of algebraic manipulation, we can apply the given information to find this integral. So if we distribute the x into the parentheses, this becomes the integral from 1 to 4 of x minus x squared dx, which splits up further into the integral from 1 to 4 of x dx minus the integral from 1 to 4 of x squared dx. Now we've been given both of these quantities. This quantity is 15 over 2, and this quantity is 21. Let's see, 40, so 32, but then 27 over 2. Oh, I hope I got that right. Next one, C. This one's a little trickier because we're integrating from 5 to 4. So these are reversed from the usual order. And reversing the order of integration negates the integral. All right, so we're taking the integral from 5 to 4 of 9x squared dx, which is equal to, if we reverse the order of integration, then this negates the integral. So it's negative the integral from 4 to 5 of 9x squared dx. And this equals negative 9 times the integral from 4 to 5 of x squared dx. And let's see, we've been given this quantity is 61 over 3. All right, so that's, let's see, 183 except negative. All right, finally, this one is much easier than it looks. So I don't want to actually integrate this function because I noticed something about the bounds of integration. They're both 5. So recall that the integral represents area under the curve. So if this function, I have no idea what it looks like. So if this is some crazy function, and we're integrating from a to b, then when we integrate, we get the area under the curve. We get this area. All right, but what happens if we integrate from 5 to 5? So we've got this crazy function. Okay, and we integrate from 5 to 5. This has 0 area. So no matter how complicated this function is, if the bounds of integration are the same, this integral will be 0. So how would you show this in terms of shown work? You don't have to do this whole mess that I've drawn. You can just write that this equals 0 because these are the same. Estimate the integral of this function from -1 to 3 by using 4 rectangles of equal width. And we'll use the right endpoint of let f be the function f of x equals x squared minus 5. Let's compute R4 to approximate the definite integral of this function f from -1 to 3. Here's what that looks like. So we've got the region, the zone, the interval from -1 to 3, and we're going to divide it up into 4 equal pieces. So conveniently, -1 to 0, 0 to 1, 1 to 2, and 2 to 3. This is 1, 2, 3. This is 4 equal pieces. All right. This function is not very complicated. If we have y equals x squared, that just looks like a parabola, and then y equals x squared minus 5. It's just shifted down 5. So let's sketch the function roughly. It'll help us keep track of what we're doing. So it's not strictly necessary. So there's our function. And now on each of these intervals, something like that, we're going to draw a rectangle. And because this is R4, so that's 4 rectangles, where the height of the rectangle is at the right edge of the subinterval. So we'll draw our first rectangle here. And at the right edge of the subinterval, the height given by the function is at -5. And now we'll draw another rectangle here. Where the height of the rectangle is given by the function at x equals 1, which would be at -4. At 2, looks like my drawing's not that great, because it's still negative at 2. So at x equals 2, we draw another rectangle where the height is given by the height of the function at x equals 2, which there would be at -1. And then finally, we draw one more rectangle over the 4th subinterval where the height is given by the height of the function at the right side of the integral, at the right side of the subinterval rather, which here would be, if you see, if we plug in 3, we get 9. All right, so that's at 4. All right, so these 4 rectangles give a rough approximation to the actual interval. the areas of these four rectangles approximate the integral. All right, now we add up the signed areas. What do I mean by signed areas? I mean some of these will be negative because they're below the x-axis. So we've got the first one has a base of 1 times a height of -5 plus second one has a base of 1 times a height of -4 plus the third one has a base of 1 times a height of -1, and the last one has a height of, they all have base of 1, and the last one has a height of 4. So that's -5 minus, what was that supposed to be? 4 minus 4 minus 1 plus 4, -6.